Today we're going to be analyzing the function f using the first and second derivative test, and this time we're going to be using the calculator to use the first and the second derivative test for f of x. So let's go ahead and start with f of x, or for problem number 1 we have f of x equal to x cubed. So this time we're not going to get the derivative manually. We're going to be using our Ti-84, and our calculator can give us the value of the derivative. So to find the first derivative test, we need to set f prime of x to 0. And by setting f prime of x to 0, we are generating the critical number by doing so. So to start this is your y equals, this is your graph right here. So let's plug in our function x cubed minus 3x squared plus x minus 2. And to get the first derivative of function y sub 1, you push math 8 and you push x, and vars, y vars, go to function, and you'll set the derivative of y sub 1, or you'll get the derivative of y sub 1 with respect to x. And our calculator will be generating our f of x, which is represented by the first graph or the blue graph, and also Ti-84 will be able to generate the derivative function, which is going to come out in a little while. So this is your derivative function, and we are going to be using the parabola or the red function to find the critical number. So all we need to do is to find the point of intersection of the parabola along the x-axis, and to do that, let's set y is equal to 0, and let's change the window setting to -5 and 5, so our graph will be a little bit bigger. So when we see our graph, now that our graph is a little bit bigger, now we can concentrate on the derivative function, which is the parabola opening upwards. And to find the point of intersection of the red graph along the x-axis, just push second function trace and go to intersect, and we'll find the point of intersection of the y equal to 0. So push enter as the first curve, and the second curve will be the red graph, and we can move this around. So let's put it closer to the point of intersection and push enter again, and our Ti-84 will give us 0.184. So that's our first critical number. X is equal to 0.184. And for the second intersection, we'll find our second critical number. So just push second function trace and go to intersect. Just like what we did, we're going to move this closer to the point of intersection and the red graph. And the second critical number is at 1.816. So these two are our critical number based on our derivative graph, where f prime of x is equal to 0. Now we can use our sign chart to identify our local max and local min. So we have two critical points. This is 0.184 and this is 1.816. Coming from left going to the right, the parabola. So in our calculator, we know that the derivative function, so above the x-axis, is our positive function for the derivative, and below the x-axis will be negative. So from 0.184 going to the left, 0.184 going here, we know that it's positive, or the value of the derivative or first derivative is positive, and from 0.184 to 1.816, the value of the derivative is negative, and from 1.816 going to the right, it's positive. So this is the behavior of our derivative function, which we are going to be using in analyzing our relative minimum, relative maximum, and when the graph of f is increasing or decreasing. So let's start with relative maximum. So f and for the second critical number, we have relative minimum because the derivative function is changing from negative going to positive. And with this, we can also tell the behavior of the function f. So the function f is increasing at this interval and also at this interval. So to write it out, f is increasing at -0.4 and 1.8. And also from between 1.184 and 1.816, the f prime is negative, therefore its f is decreasing. So this is our first derivative test using our calculator. So we're able to generate the sign chart by just looking at the derivative graph of our function using Ti-84. Now let's go ahead and start with our second derivative test for concavity and for point of inflection. So we are going to set f double prime of x to 0 so we can find our new set of critical numbers. We don't need to solve it by hand. We're just going to be working on our calculator. So we're going to use the calculator for our second derivative test. So this is the graph of the first derivative. This is the original function. Now to graph the second derivative, we can set y sub 4 as our second derivative by taking the derivative of y sub 2. So we'll push math 8, and set this to x, and then this will be y sub 2. So vars, y vars, function 2. So now y sub 2, or we're taking the derivative of y sub 1. Y sub 2 for the second derivative, and this is going to be x. And since we don't need our first derivative, I'll turn it off by pushing enter. So now this is turned off. I will also turn off the original function because we're just going to be using our second derivative and the function y equal to 0. So we can find the point of intersection of the x-axis and the second derivative. Now we have the graph of our second derivative and y equals 0. Now we are seeing that we have the positive value and the negative value over here. So this is the positive value of the second derivative, and this below the x-axis is the negative value of the second derivative. So to find the critical number, we're going to find the point of intersection of the second derivative graph along the x-axis. So just like what we did, second function, trace, go to intersect, and this is our y equals 0, and this is our second derivative graph, which is y sub 4 in our Ti-84, and it's giving us 1 as its point of intersection. Therefore the critical number for the second derivative test is 1. So we're going to be using that as our new sign chart, but this time it's for the second derivative. So we know that on the second derivative, number below 1 will be negative since the value of the second derivative graph is negative, and from 1 going to the positive infinity is going to be positive. So now we can use our sign chart for the second derivative to give or determine the concavity and the point of inflection. So let's start with concavity. So we know that it's concave down from 1 to the negative infinity, and we know it's concave up from 1 to the positive infinity. So to write our answer, F is and for concave, I'm sorry, this is concave down. And concave up, since it's positive. And also, we know that the point of inflection exists because the concavity is changing from negative to positive at x equal to 1. And this is how we analyze function f using the first derivative and the second derivative using our Ti-84. Now let's go ahead and answer problem number 2 for a trig function. We have f of x so we know that sine squared x is the same as sine x squared, because this is the notation that we're going to be using in our Ti-84 when we graph it. So let's go ahead and find f prime of x equal to 0, which will help us find the critical number for our first derivative test. So to do that, go to y equals, and since we already have the first derivative, the second derivative, and 0 from our first problem, all we need to do is to plug in our new function. So we have sine, or parentheses, sine x squared plus sine x. So this is our first function, sine x squared plus sine x, and let's turn on graph number 1, which is the original function, graph number 2, which is the derivative function, and y sub 3 is equal to 0, which is our x-axis. So let's turn off y sub 4, which is the second derivative, because we don't need it yet. So also, we can also change the window from 0 to pi, so we can have the graph from 0 to pi, so it will be a little bit bigger. So let's graph it. So now we can find the critical number by finding the point of intersection of our red graph, represented by the first derivative function, and y equals 0, which is the x-axis. So second function, trace, go to 5. This is the blue graph. We need the red graph. Push enter. And this is our x-axis. Push enter. And Ti-84 will give us the point of intersection of our derivative function and the x-axis, which is 1.571. So now that we have our first derivative, we can now construct our sign chart. So our sign chart So from our Ti-84, we know that from the left of 1.571, the derivative function is positive, and to the right is negative because it's below the x-axis. So this is now our sign chart, which we can use in writing out or finding out our relative min and relative max. So here we only have one critical number, so we have relative maximum because it's changing from positive to negative. So going up, and then it went down right here, so we have a maximum. So F so we don't have a relative minimum, just a relative maximum. And to write out the behavior of our function, F is so this is now our first derivative test for this function over here. Now let's go ahead and use the same calculator or Ti-84 for the second derivative test. So in the second derivative test, we're going to find the concavity and the point of inflection of the function f. So to do that, we need f double prime of x, and we need to set it equal to 0, so we can have our new set of critical numbers. So using our Ti-84, so same function, we are going to turn this off. We also going to turn off the original function and turn on y sub 2, y sub 4, which is the derivative of y sub 2. So our calculator will compute for so now that we have our second derivative and y equals 0, let's find the point of intersection. We have two critical numbers for our second derivative test. So find the first critical number, second function trace, intersect. Let's find this one first. And the first critical number is at x equal to 0.635. And the second critical number (2.5067) or x equal to 2.507. So this is now our second derivative, and we are going to use the two critical numbers for our sign chart, and this time it's for f double prime. So this one is for 0.635 and this one is 2.507. And we know that it's positive because it's above the x-axis on this interval, negative because it's below the x-axis, and above the x-axis, positive for the second derivative. So now that we have our sign chart, we're ready to determine our concavity and the point of inflection. Let's start with concave up. So this one is concave up, going up and going up, and this one is going down. So there we have two concave ups, or interval for two concave up. And since we have two critical numbers, and on this critical numbers, the concavity is changing for both critical numbers, so we have 2 point of inflection. So our POIs will be at x equal to 0. So this is our analysis for the function sine squared x plus sine x on the interval 0 to pi using TI-84.